Hello everyone, welcome back to our channel. In our channel, we discuss the usage of various open source softwares. In this lecture, I'm going to talk about CFMesh. In CFMesh, as you might have seen in our previous lecture, that CFMesh can produce better mesh compared to snappyHexMesh for some of the geometries where snappyHexMesh fails to capture sharp features. Let's get started. First of all, let me show you the website from where you can download CFMesh. You can search CFMesh on Google and you can download a version for Windows as well as for Linux. You can also download the source code of CFMesh, and here you can also download the documentation for this. Here is the user guide. It is a pretty simple user guide, only 24 pages, and here it talks about that what are the meshing workflow. You can check that how it creates the mesh. I'll discuss this. We'll use this documentation to go through various meshing techniques that you can use to create meshes. We are only going to talk about 3D meshing, not 2D meshing, but you should note that 2D meshing works only along this. So the geometry is given in a form of ribbon in the XY plane and extruded in the Z direction. It does not work in any other direction. Please take a note of this, and then we'll talk about only 3D. There is a tetrahedral mesher as well, and we are just going to focus on Cartesian, which is the 3D one. First of all, we'll talk about the input geometries. It requires a list of points, list of triangles, patches, and facet subsets, and featured edges. These edges you can extract using this particular application, which is provided with CFMesh, which is surface feature edge. And this is the format that it creates. You don't have to worry about this. When you want to create a mesh for something which is an internal flow, for example, this particular object, this is for finite element method, but let's say this is a pipe and you want mesh inside this, then you need just the geometry. But if you want to perform an external flow, in that case you have to create the domain as well as the object on which you want to perform the meshing, and always make sure that the normals are always pointing out of the geometry. For the outer domain as well, it should point out of the geometry. However, CFMesh can generate meshes for those kind of geometries as well. Now, first thing that we are going to do is we are going to create the geometry. You can go through this. I'm not going to discuss this further, and I'll just show you that how you can perform various steps. And this is what we have done in our previous lecture. I used the same geometry. I'll just discuss that how we have created this. We have used Gmsh software. In Gmsh, if you open this triangle.geo, you'll see that it has two geometries. One is the smaller one, which is inside, and the outer one, which describes the domain bounds. I have also created a 2D STL for this, and you have to make sure that after creating, you are assigning a physical surface to those inner and outer geometries separately. And when you are exporting this, let me show you that if you export as is, I'll export this as triangle.stl and I'll do this as a single solid. If you just look at this triangle.stl, you'll see both the geometries. It looks fine. Both the geometries are here. And when you create the mesh, you'll see that it generated the interior as well. When you export this without this physical surfaces as different STL, you can still generate the mesh over the outside of the interior one and inside the outer domain which you want. But in this dictionary, sometimes we want a finer resolution for the inner and a coarser resolution for the outer. That you cannot set if you don't have that. This is not working. You can see the local refinement. If I change this, use the surface feature as triangle to FMS, and let me run this again. If you reload this, the outer domain looks fine, and in the interior you can still see the inner object. But if you look at the resolution there, it's huge. It's same as what we have here or here. It's the same, but it's taking this value. It is not taking the local refinement. Let me export this geo, create the mesh, and then while exporting, you select per physical surface. When you do that, the STL will assign different labels to different surfaces that we have assigned in Gmsh. And now if we again convert this to FMS and again run Cartesian mesh, then you can see that it has a finer meshing close to this. If this much is clear, then let's talk about various other features that this CFMesh offers. We'll start from the global parameters. These two are the mandatory ones. If you don't give these two, it won't run at all. Then you can also have some refinement settings, like you can set that what is the boundary cell size. These are useful when you have an internal flow and the boundary is only the boundary where you want to capture the high gradients of the velocity. But for the case that we have right now, you cannot use this directly. Let me show you why. Let's say at the boundary you want 0.01. Let me run this. Now you can see it was like this before, and if I reload, then there will be finer meshes here as well. For all the boundaries, it assigns the same resolution, the same cell size that we have written here. Clearly we don't want this, so I'm not going to use this. Then the next thing is, let me use this again, but with little bit higher cell size so that we can show some other features. We can also have boundary cell size, refinement, thickness. This is the distance up to which this cell size will be effective. If I set this as 0.1, then up to 0.1 distance, this cell size will be effective. Again run Cartesian mesh, and now let's see here. Right now, whatever is the cell size is limited to this. Now let's say 0.1 is up to this point, then we'll have this resolution up to this point. Now you can see the resolution has some thickness. Now you can also have a minimum cell size. If you set this, then it will try to capture the features. I'll just remove these two. Let me make this 0.1 and run with these two only. Now let's see what happens. Clearly it tried to capture some important features by a very fine resolution, and where the feature was almost flat, it did not refine. This adaptively changed the resolution. Where the features were sharp, it used a lower cell size, and where the feature were smooth or flat, it used a larger cell size. This kind of parameter will help in those cases where you don't want to specify specifically what you want at some corners or similar to that. But like before, as I said, that this again you cannot use for external flow because we don't want a fine resolution here. This is the domain exterior. We don't want a fine resolution here. Therefore, we want some local control. I'll again switch this off. So these three we can use for internal flows, but for exterior flow, these are not that useful because it will do the same thing to the domain boundary as well. Now let's look at local refinement, which is this. In the local refinement, you can set the cell size for different patches that are present. Patches you can have by assigning the names in your surface mesher. Here we have used Gmsh. In Gmsh you can do it using this. And along with the cell size, you can also define the refinement thickness, which is again, let's set this to 0.2, and here I want the refinement thickness as say 0.5. Let's again remesh. Now reload. You can see that up to this thickness it assigned this resolution, and For the outer up to this distance, it assigned this, which is clearly visible in the mesh as well. Right. Now let's look at some other features. You can also have object refinements. For example, let me change this to 0.1 and 0.1, or let's make this no refinement thickness. Whatever is the cell size we have set here, it will just make sure that this surface is of this resolution and then gradually decrease the as short possible distance. You can also have object refinements. Here you can have any name, for example box 1. There are various shapes that I'll discuss in a while. Here you have to set the type, which is box, then the cell size in the box, let me set it to 0.02, and then the center of the box. Since our box, this particular domain is at 0, 0, 0, I'll set this new center at 0.2, 0.2, 0.2. Similar to OpenFOAM, you don't put comma here, and the length in different direction. Length is 0.1 in x direction. These syntax you will find in the documentation. In y direction 0.1, and similarly in z direction I want 0.3. It will create this box. Inside this box it will make sure that this is the refinement. Let's try this. The spelling is this. Now if I reload, clearly this refinement is not that clear. I'll change this to something finer. Still not that visible. Let's look at some other slices. Maybe it is not that visible in this particular direction. Here it has a better visibility in this direction. Let me take another slice in the third direction. In this direction you can clearly see the patch. This one is the patch that we have created. This one is the refinement zone. In a similar manner, you can have different shapes. The shapes that are present in CFMesh are cone, and then a hollow cone, as well as a line. There is sphere as well. For that you have to put center and then radius and then refinement thickness. Let's see if we can put a refinement thickness here. Refinement thickness. Clearly the refinement thickness works for this as well. This was about refinement zones that you can create. For example, a wake zone you want to capture, you can have a refinement zone there. I'll switch this off and let's move to another parameter. The next one is surface mesh refinement. Similar to object refinements, you can also have surface refinement. So let me create a surface first. Let's try to use this one, which is this surface. Let's see where it lands on the original geometry that we have. It's here. Now we'll use this particular geometry and we can have a refinement on this surface. Let's see how we can do that. I can do that by typing first the surface mesh refinements. Inside this you can type anything like one surf, anything, and inside this you have to type the surface file. So the surface file is bl.htl. I'll copy this. Then you can tell the cell size. Cell size is something that we have used before. You can also say that what is the additional refinement level. So if something is x, it will do x by 2. If I set it by 2, additional refinement levels. If I set this to 3, it will do x by 2, then by 2 again. Then you can again have refinement thickness. I'll set this to 0.1. First, let's copy bl.htl here. Now I'll run Cartesian mesh. Let's reload this. All the refinements are gone. Now I'll move this particular clip, which is this one, to this surface. I don't see any benefit here. Let me move this to that surface, to this one. Let's try cell size instead of this. Cell size equal to 0.0105, and now try. And one thing to note here is if there is some typo or some mistakes, for example, I type blah is 0.1. Cartesian mesh does not show any error. It won't tell you that there was some error. It will just ignore that or don't run that at all. That's a downside for this. If you have a typo here, let's say you don't put levels, you just write level, it won't tell you. It will just won't run this at all. So make sure that you understand this and don't make a mistake while typing. Again, no change. Let me check if we have done some spelling mistakes. This should not be S. We found one. Everything else looks fine. It's loading. Now clearly you can see around that surface we have a very fine mesh that we have set. This kind of technique you can use to create very fine mesh around a weird looking surface as well. This is very useful. Now next thing is keep and remove cells. You should have very thin gaps and then only we can simulate this. CFMesh gives you option to keep some of the cells which are intersecting a very thin surface. So you can say that for this particular patch, keep the cells in this patch or do not, because the gap is very small. In that case, you can tell that whether that gap is actually a gap or not to CFMesh. This we are not going to discuss. So you can try on your own. The next thing that we should discuss is boundary layers. Here, globally you can define n layers, let's say 5, and then thickness ratio 1.2, then max first layer thickness, let's say 0.02. This is just the maximum value it can have. If you set this to be very low, then your first layer will be very fine. This is a global parameter. See what it does to your mesh. When you set this as a global parameter and your simulation is an external flow simulation, then there is a problem. You can see here. If I reload this, you will see that, let me switch off all other things, just this one. It has not created any layers, I guess. Let's see if we have done some spelling mistake. This should be boundary layers. Again reload, and you can see it has created nice looking layers. And in the crinkle slice, on the slice, go to crinkle slice, you can see the actual layers that has formed. But before this, you should also note that it has created layers on the exterior of this as well. Therefore, similar to what we have done here, you can also have locally defined layers. This should be inside this, and you can have patch boundary layers. Inside this, you can define inner as a dictionary. So this cannot have any name. This should have a name which is already there in the mesh, like we have here, the inner. Define inner here, then I can say n layers are 5, then thickness ratio is 1.2, and max first layer thickness, which is 0.02. And again run this, and you will see now that the outer layers will be removed, and in the inner geometry we still have the layers. So in this way you can control where you want the layers and where you don't want the layers. There are some optimization parameters for the layers that I'm not going to discuss because this is a very simple geometry, but you can go through the documentation for that. The next thing is sometimes you require anisotropic geometry somewhere. For example, your flow is along x direction, it's uniform along x direction, but along the y direction it's non-uniform. You want a higher aspect ratio cells. In that case, you can define anisotropic sources. We can define a box 1. Inside this box you have to write the type of this. You can also have planes. There are only two types that you can define in CFMesh. One is box, another is plane. Type here, then the center. Center is same as we have chosen before. Length x, length y, and length z. And then you can define the scale. This is very important, that what should be the scale in various directions. Let's say in x and y I want 1, in z direction I want say 0.01. Let's see what happens. So right now our slice is in the YZ direction. In the Z direction the mesh should distort. Let's do this. Let me also make sure that there is no spelling mistake. It looks fine now. Let's run this again. Clearly it is something very non-trivial and hard to create mesh on. Let me change this to something which is not that extreme. So now this ran fast. Now when we reload, we'll see that it changed the size of the meshes in a certain patch as it's visible easily. Clearly this is useful for layers as well. Let's say for the layers you want them to be growing in certain direction, or the flow does not have a high gradient in this direction, you can have high aspect ratio cells here. In that case you can do this kind of anisotropic meshing. Then the second last thing which is there in CFMesh is, you might have noticed that there are various steps where you may want to debug where the error was, whether it's the surface, where is it's the solver, or what's the problem. So there is a simple debugging method that is present in CFMesh. You can pause the program in between using this particular dictionary. So you can type workflow controls and then you can write stop after say template generation. There are total 8 stages. I'll stop in each and every stage and show you that what are different stages that are possible. And I'll also discuss that how it is different than snappyHexMesh. It will also restart from what it has done already. This particular key is used for that. Create the Cartesian mesh, and then let's look at this one. Let's activate crinkle slice here. So you can see that the cells are created according to whatever resolution we have here, and they are aligned with the axis. Axes are aligned in this direction. The blocks are also created in a similar manner. This is somewhat similar to what is done in castellation in snappyHexMesh. But the next step is surface topology in CFMesh. So I'll change this to surface topology. Let me check if I spelled it correctly. Now if I run this again and reload, there was not much change in the surface topology step, so I'm not sure what it does in this particular step. The next step is surface projection. In this particular step, which is surface projection, unlike snappyHexMesh, which projects as well as cuts the cell, it projects all the surface points to the surface. Let's see that after template generation. This was not saved, so surface projection is done now. I think the previous step was not done previously. Let's reload files, and you can see that the surface projection is successfully done and you have the actual surface of the geometry that you want to capture. Now the fourth step is patch assignment. that we can skip. It assigns the patch. We can say that the inner patch is something else and the outer patch is something else. That sort of stuff you can do in patch assignment. Then there is a step on edge extraction. If there are some edges that you want to capture, then that particular step is performed in that. Then the next step is boundary layer generation. I'll do that. Boundary layer generation, and again run. It stopped after boundary layer generation. In this step, the boundary layers will be generated. So now you can see here the boundary layers has been generated. And then the next one is mesh optimization. It optimizes the mesh and then it refines the boundary layer. Probably in the boundary layer refinement, it refines according to the requirement. Let me do that. Boundary layer refinement. This is the final step. If I reload this, clearly that was just the boundary layer generation, and in the boundary layer refinement, it refines the boundary layer according to the number of layers and the growth ratio that we have set. This is how you can debug various steps and what is causing the problems. And in order to check that, you can always run CFMesh after each and every step and see whether the mesh quality is good or not. This should be less than 3, and similarly the orthogonality should be less than 70, the maximum orthogonality, and this should be around 10. Clearly this is a good mesh. The last thing that you can do is you can rename the patches. So the correct syntax to write that, you can refer to the documentation. There is nothing new there. You can also enforce the geometry constraint by typing this geometry constraint. When this is set as 1, it will capture all possible constraints. It makes sure that your geometry is captured with as high accuracy as possible, but this always comes with a drawback that it sometimes can deteriorate the quality of the mesh. So this is an optional feature, you can try that. And then there are various libraries or utilities that are provided with CFMesh. The one you can always try is improve mesh quality. So after running this, you can try improve mesh quality, and it will try to improve the mesh quality. Now if I run CFMesh, you'll see that it tried to reduce this. Remember that this giving you a good value does not mean your mesh is good. You have to make sure that it also looks good, it has proper y plus values that you want, then only your mesh will give you a good solution. With this, we'll stop, and if you like the content of our channel, then please like, share and subscribe. Thank you.